Welcome again to this series of short videos on the development of our understanding of atomic structure. In the previous video in this series, linked in the description below, we investigated the key experiments at the turn of the 20th century that led to the understanding of atomic structure and hence the periodic table and reactivity. The last of these was Niels Bohr and his development of what is called the planetary model. One reason through his experiments that, much like the planets, electrons traveled in set orbits around the nucleus. However, Bohr only looked at the distance between those electrons and the nucleus. This creates a problem, because distance creates a potential energy. In the case of the solar system, if the planets weren't moving, gravity would suck them directly into the sun. In the case of an atom, if the electrons weren't moving, positives and negatives would attract. The only way the system of orbits can be stable is if the particles participating in them are actually having movement, and they are developing kinetic energy to balance out the potential draw of the center. In the case of the atom with the orbit of the electrons, Bohr was right in his first estimate. There is an orbit level. N is the principal quantum number. It's called the energy level or the shell of the electron. That electron can be any given number of set distances away from the nucleus. This provides a potential energy to the negative electron and the positive nucleus that's inversely proportional to the distance. In order to balance this, these orbits, which can have any integer value from n equals 1 and forward, have to be balanced against an orbit which shows kinetic energy as angular momentum. This is called the quantum number L. L actually defines the shape of the orbit, hence the term angular momentum. Most orbits are thought of as round. The value of L, however, can have multiple values because there are multiple pathways possible. In addition to a round pathway or a circular pathway, you can do a figure-8 loop, which is why L can have any integer value from 0 up to n-1, where the number of values that one develops equals the number of pathways available. So you could travel in a circle, or in a figure-8, or in a loop, or any more complicated shape. These shapes are called the orbits. If one looks at a given distance at an energy level, at n equals 4, that means L can have the following numbers. L can be anything from 0 up to n-1, so it can have a value of 0, 1, 2, or 3. L equals 0 is what's called an S orbit. The S orbit is perfectly circular in shape. And is actually spherical in 3 dimensions. L equals 1, a P orbit, winds up giving a racetrack or a figure-8 shape to the movement. L equals 2, which is called a D orbit, winds up giving a shape similar to a 4-leaf clover, where the electron travels along a 4-way path. L equals 3 is an F orbit. Essentially gives a complicated shape similar to a chrysanthemum. It's a multi-leafed flower having 7 different lobes. The meaning, historically, of the letters S, P, D, and F had to do with the spectrum emitted by the atom as the electrons moved. The shape of the lines that were seen in the spectrum, S indicated a sharp transition, P, primary, D, weak and diffuse, and F stood for a fundamental line shape. So, you have N giving the potential energy rather, the distance from the nucleus. L gives the angular momentum, gives the shape of the electron, as the shape of the orbit rather, as the electron moves. Once there is shape, direction winds up being implied. This leads to the next quantum number. For example, if I have L equals 0, an S orbit is spherical. In this particular case, it doesn't matter in which direction the electron's moving, it will always wind up in the same spot. However, when I move up to L equals 1, I have a p orbit, which is a figure 8. This is essentially a two-dimensional shape, which means it can be facing any one of three directions. It could be either laying on the x-axis, the y-axis, or the z-axis. Those three possible orientations lead to the next quantum number in the series. This is called m subscript L, or m sub L, and is the magnetic quantum number. It can have any integer value between negative L and positive L. The number of these values that are obtained give the number of possible orientations. So once again, each one of these orientations corresponds to what orbit one is in. If L equals 0 rather, and I have an S orbit, m sub L can only be equal to 0. Since that's only one number, there's only one possible direction or one orbital corresponding with the S level. For the p orbit, if L is 1, m sub L can be minus 1, 0, or plus 1, giving three directions. For the d orbit, m sub L can be minus 2 all the way to plus 2. This gives 5 values and 5 orbitals or 5 directions. For the f orbit, at L equals 3, m sub L can be minus 3, minus 2, minus 1, 0, 1, 2, or 3. This gives a shape that can be laid out in 7 possible ways, given 7 paths to an f orbit, or 7 suborbits, or orbitals. So in summary, the orbit of the electron, its very position, is first of all given by the principal quantum number. This can have any positive integer value and essentially correlates to the potential energy or the distance from the nucleus, the energy level that that electron is in. This needs to be balanced by motion. Your second quantum number, L, gives that motion. It gives the angular momentum and the shape of the orbit. L can have any integer value from 0 to n minus 1, and as the angular momentum has to balance the potential energy, you'll notice the value of L depends on the value of n. Once one does have angular momentum and motion, one also now has direction that one can move in. Hence, the third quantum number, the magnetic quantum number, m sub L. This can give any values from negative L to positive L. It corresponds to the various numbers of pathways that are available for a given shape in the orbit. Therefore, the value of m sub L depends upon the previous value of L. Essentially, at this point, we are mimicking the behavior of planets in the solar system. They are a set distance from the sun, and they do orbit to balance out that potential difference. There is one other motion that planets do that electrons also do. Just as the orbit of the Earth gives us the year, the Earth is also rotating on its axis to give us the day. In the case of an electron, this is called spin, and it can come in one of two different directions. On its axis, the electron can either spin clockwise, or it could also spin counterclockwise. Those two directions correspond to the fourth quantum number. The fourth quantum number is called m subscript s and only has two values, plus 1/2 and minus 1/2. Starting with Niels Bohr's orbital theory of the electron, we now find out that the position of any given electron can be determined using four sets of numbers, essentially an address. N, any integer, which tells you the energy level or shell the electron happens to be in and how much potential it has. L, the angular momentum, the shape of the orbit that's balancing out that potential, can have any integer value from 0 up to n minus 1. M sub L, the magnetic quantum number, tells you what direction, essentially, that electron is orbiting in, and has any integer values from -1 to +1. L depends upon n, M sub L depends upon L, and the final quantum number that's available is spin, where M sub S can either be +1/2 or -1/2. So every single electron on every single atom is defined by four quantum numbers: N, L, M sub L, and M sub S. These quantum numbers, as you will see in the following video in this series linked below, give each electron its own unique address and also determines how many electrons an individual atom can have and where they are within the system of that atom. Thank you very much for listening, and I hope you found this information useful.